Okay, what we did last time. Transformations from R2 to R2, R3 to R3, R3 to R2, R2 to R3. The idea is extend transformations from Rn to Rm, where n and m could be any numbers. Okay? R2 to R2, need a 2 by 2 matrix. R3 to R3, we define the transformation by 3 by 3 matrix. And any linear transformation can be defined by matrix. Okay? Now there are linear transformations you haven't thought of, like derivatives of linear transformation, but nobody knows what that is yet. Okay? R3 to R2, what kind of matrix would you need to go from R3 to R2?
A 2 by 3 matrix.
It has to be 2 by 3. Your rows have to be 3 units long, and you need 2 of them. Rows have to match vectors in R3, and you need 2 of them to get a vector in R2. And of course, you have a 3 by 2 matrix here. Okay? Sometimes, for R2 to R2, the transformation could take all of R2 to all of R2. Okay? If the matrix reduces domain is R2, range is all of R2, okay? If the reduced form is it could be 1 star, 0, 0. That's for a 2 by 2 matrix. The domain is still R2.
For clarification, based off of what you have underneath, so the idea is extend to R to the N becoming R to the M, that would be an M by N matrix.
Yeah.
Okay.
Yeah. Yeah. Okay. If it's this, your range is a set of all vectors. Well, I'll just say the set of parallel vectors associated with a line through the origin. If you don't totally understand that, and you don't totally remember what we did last time, but you will when you go back and think about it, right? We illustrated it quite completely, okay? And then you can make similar statements about transformations from R3 to R3, or R, okay? Then you talk about planes or lines for all of R3, okay? So I'm not going to write down these, but if you've gone from, let's say, R3 to R2, and this is something we want to look at today, okay? Just trying to figure out where I'm gonna write this.
Have you seen the podium?
He's looking for the podium.
Actually, we need more room,
The
so.
one that's in my
Um,
picture is very
I'll come down here.
I'm gonna correct stuff on it.
Your matrix could reduce to this form. Of course, this is a reduced matrix, right? Could have this form. Could have this form. Okay. The domain is clearly R3. Write a transformation like this. Here. The range is, wait a minute, this is R3 to R2. So R3 to R3, so I was doing R3 to R3, even though I knew I was going to do R3 to R2, and wrote it down like that, right?
Now you don't have to write an example for R3 to R3.
Well, I just take out the third row in each case. And I don't need this matrix. It'll essentially be one of these two, although there are other versions of these, and we'll worry about that later. But they're basically two possible cases. So we don't have the range as all of R3 because the codomain, the second space, is just R2. Range is all of R2. And over here, geometrically, the range is associated with the line at R2. And it goes along a set of parallel vectors. Okay? Make sense? Okay? Now there's more to it. But let's look at R2. R3. The domain is all of R2. Okay? Now you could have okay? In which case your range would be a plane at R2. Okay? I can say more about that. The range consists of all the vectors you can get by adding multiples of two vectors that are non-parallel. Okay? Now say this is a sum of two non-parallel vectors, okay? Set of all possible sums of multiples. I have to smudge it, multiples of so you got two non-parallel vectors. And the only thing that matters about these two vectors is their directions. Okay, they can be longer, they can be shorter. They just don't have the same direction. Okay? And then all the sums of multiples of these vectors. Okay, so you go along this direction, then you go along this direction, and you get a vector. And that's a plane. Okay? And if you have this, it's a line in R3. Okay, now by line in R3, that's an abbreviation for a set of parallel vectors associated with a line through the origin of R3. Okay? So I'm abbreviating this statement here and abbreviating it even more here. And you can't have the range being all of R3. Can't have, no, we've got to prove that. So that's kind of what we're looking at. Okay? It's basically just do a linear transformation of R2, you can't get something more than 2 dimension. We would need to find dimension. We're working toward it. Okay? Now if you got Rn to Rm, there are all kinds of possibilities if n and m were big enough number. Okay? But it's just an extension of these ideas. Okay? Now there's more. Okay? So, additional things. If you're going from R3 to R2, you basically got 3 dimensions collapsing down to 2. Okay? So, if you go from R2 to R3, okay, there's a whole set of vectors in R3 that you can't get. Okay, in this case, it's a set of vectors perpendicular to a plane. Okay? In this case, it's a plane perpendicular to this line. Okay? So, also, first place, it should be clear that the 0 vector is always going to map onto the 0 vector, right? 0 vector of this space always maps onto the 0 vector of this space, because if your column consists only of zeros, your products consist only of zeros. Okay? A good question is, what vectors in space over here map to the 0 vector in the space over there? Okay? So, question. For transformation from a vector space V to vector space W, where you could think of V as Rn and W as Rm, right? Just 2 different real spaces, and you can come back and think about one of these, because anything you think here extends in a pretty natural way to higher dimensions, okay? So you can always come back to your intuition and your picture of 2 and 3 dimensions, okay? Okay? We call that set, we have a name for that set, it's a very important set. It's called the null space. These are null vectors. Okay? Well, let's just do an example. Let's take transformation from R3 to R2. Now I'm going to lay notation on you. Actually, I'm going to do it just for an actual matrix, okay? So let's say the matrix is 2, 4, 1, 1, -3, 2. Clearly, this row is not a multiple of this row, so that the reduced matrix is of the form this. Okay?
Is that -2?
I'm sorry?
Is that -2, 4, 1?
Where?
Right that one. Or
T
it
is the
just-
transformation.
No, I mean, underneath the actual matrix, is it -2, 4, 1 or 2, 4, 1?
It's 2, that's like a smudge. Although if it's -2, that'd be okay. Okay? Okay, so it reduces to this. Okay, what we're looking for now is the null space. X is a null vector. If and only if AX equals 0, right? Okay. So, let's write that out. We have 2, 4, 1, 1, -3, 2, multiplied by x, which I'll designate now by column vector x1, x2, where x is a vector, x1 and x2 are the numbers that make it up. That equals 0, 0. And mapping from R3, I started to do the multiplication. Oh, wait a minute. Okay? Wrote it down carelessly. Okay? So, we could then proceed to reduce an augmented matrix. 2, 4, 1, 0, 1, -3, 2, 0 matrix. Because you know that's, when we reduce that, we get a matrix that indicates the solutions. And we would get 1, 0, star, 0, 0, 1, star, 0. This star is the negative of your x1, and this star will be the negative of your x2. Because this equation says x1, okay? Well, it actually gives you the relationship between x1 and x3. Okay, started to say that wrong. We're gonna do the equations though, so we can see clearly what I just said wrong, okay? So we have 2x1 plus 4x2 plus x3 equals 0, and x1 minus 3x2 plus 2x3 equals 0, okay? Now that reduces to this. Just a second, I just switched, so the second is now the first. And then I add -2 times this to this, which gives me 0. And then -2 times this is 6, and add that to 4, we get 10x2. And then -6 times this, -2 times this is -4. We add that to the 1x3, we get okay. Then we can divide this one by 10. We get x1 minus 3x2 plus 2x3 equals 0. And we get x2 minus 0.3 x3 equals 0. Then we add 3 times this to this. Let's hope I do my arithmetic right. But we get x1. 3 times this is -0.9 added to 2. Get this. Okay? So, x1 is -1.1 x3, x2 is 0.3 x3. Okay? Make sense?
I feel like I missed a step somewhere in there.
Well, you can fill it in. You know how to do this. Okay? Not going to worry about the details of the arithmetic. I could even be wrong. I could have made a mistake here. I don't care. Okay? We work it. But I'll ask you to work one for yourself. Okay? I mean, I do care. I'd rather not make silly mistakes. I was fairly careful. I'm pretty sure of my steps here. But there were a lot of them, so 70-30, I think I did it right. Okay? Actually, a little more confident than that. Okay. What's this mean? x1, x2, x3 equals this. Okay? Okay. So, you know, vectors consist of all scalar multiples of -1.1.31. Very specific vector. in R3. Okay? Means all vectors that are multiples of this are going to be transformed to 0. And you can check that out. You can check if I did it right. Just multiply this vector by this matrix and see if it works. Okay? Of course, it could be any multiple of this vector, right? Say the same thing for multiples of this, so you don't have these decimals. So you can think in terms of integers, right? Sometimes it doesn't hurt to think in terms of decimals. Sometimes it's easier to think in terms of integers, especially if you're going to multiply by this matrix. If this matrix times this vector gives you 0, then this matrix times this vector has to give you 0. And this matrix times any multiple of either of these vectors gives you 0. Well, let's see if it's so. 2 times negative 11 is negative 22. Not going to work. Oh yeah, it is. 3 times 4 is 12. Negative 22 and 12 is negative 10. 1 times 10 is 0. So I'm 95% sure I did everything right. Actually, I go about 98 or 99. But we want to check the second row, right? So negative 11 here. Negative 9 here is negative 20. 2 times 10 is 20. Bingo. I actually did one right. We could just call off class and have a celebration. We need to move on. Okay. Now, make sense? Okay? So I'll just say multiply by the A matrix to check. Okay? We got 0, 0, so we're okay. Well, the other question then is, where are the rest of the vectors in R3? Okay? Well, they're all the vectors that turn out that are perpendicular to these. Okay, so let's answer that question in terms of, set of calculations. Okay? So, okay, well, I was going to say some thoughts are fleeting. I'll come back to it, I'm sure, but this would have been a good time to say it if I remember. Oh yeah, the reduced matrix, of course, could replace all this. You know, your reduced matrix would be 1, 0, 1.1. So this star would be 1.1, this star would be negative 0.3, right? So matrix reduction would have given us right, meaning, just to remind you, because we've done a lot of stuff, meaning just the same thing we got from doing the simultaneous equations. Okay? So you always have to remember that the matrix reduction represents a set of simultaneous equations, and you could write it out either way, just the matrix reduction is a little more compact. and we can express results in terms of the nature of the reduced matrix. So now we know if the reduced matrix looks like this, then the set of null vectors is what we get when we add a column of zeros. Here, augment the matrix with the zeros because of this says. Okay? This tells us this. This gives us this a matrix that reduces to this. Okay? And the matrix that reduces to this is just this matrix with the zeros. We don't want to lose track of that. Lose track of that, we lose track of what everything means, and we're not going to see the things that we need to prove the things that we need to prove and to get the results that we need to get. Okay? So we've got that. Well, let's go to the question now of where are the vectors in R3 that don't map to the zero. Okay? Well, okay. And that is just a question of, well, yeah, I'm going to tell you, don't set it up and do it. So we'll do that. This one's gotten long enough.